Hello everybody. Let us now look at module 5 in EC368 Robotics. One request would be to keep your notes along with you in order to follow the symbols and the derivations clearly. So keep your notes as you follow this video. So we are now going to look into the first part of module 5, that is velocity kinematics. Velocity kinematics deals with velocity relationships. So far in module 4, we had talked about forward kinematics and inverse kinematics. Now, velocity kinematics deals with velocity relationships. It relates linear and angular velocities of the end effector or any other point in the manipulator to the joint velocities qi. We know that joints can be of two types, prismatic joints and revolute joints. For prismatic joints, qi will be equal to di, and for revolute joints, qi will be equal to theta I. So we are going to relate the linear and angular velocities of the end effector or any other point on the manipulator to the joint velocities qi. So before we start off on deriving these relationships, let us look at a few of the results that we will require. These results have been proved mathematically. I'm just going to summarize the results that are required for continuing with the topic velocity kinematics in this lecture. So the first thing that we would require is the definition of angular velocity. Angular velocity can be written as omega is equal to theta dot into k. K is the unit vector in the direction of the axis of rotation. So if there is a rotation, the direction of the axis of rotation is represented by the unit vector k. Now theta is the angle swept in the movement in the rotation. The angle swept is theta, and so d theta by dt or theta dot is the time derivative of the angle swept. Now we saw in the previous slide the definition of angular velocity omega. Now looking at the definition of linear velocity, the linear velocity of any point on the body can be written as v is equal to omega cross r. Okay, the linear velocity v is equal to the angular velocity omega cross r, where r is the vector from the origin to the point. Okay, so r is the vector from the origin to the point. So these are the two definitions of linear and angular velocities that we are going to use. Now another very important thing that we will be requiring in the velocity kinematics is the concept of skew symmetric matrices. As we all know, skew symmetric matrices obey the relationship S transpose plus S is equal to 0, where S is a skew symmetric matrix. So if you have a matrix S, if S transpose plus S is equal to 0, then it is a skew symmetric matrix. So we can write for any vector A, AX, AY, AZ transpose, okay, we can write the corresponding skew symmetric matrix of the vector S of A as this format. This is the format for the skew symmetric matrix for this particular vector. So you can see the diagonal elements are 0 and you have minus AZ, AZ, AY, minus AY, minus AX and AX. So this is the format that you should remember. So as an example, let us see. So I corresponds to unit vector that we commonly associate with the x-axis. So I is equal to 1, 0, 0 transpose. So the skew symmetric matrix corresponding to I. So we know that except for AX, all other elements are 0. So the three diagonal elements are 0, minus AZ, AZ, AY, minus AY, AY minus AY is 0. This is minus AX. So AX is equal to 1, so minus 1 and AX is equal to 1. So you have 1 here. So this is the skew symmetric matrix corresponding to the vector I. An important result, what is important about the skew symmetric matrices is, if we have a rotation matrix R, okay, K theta, that is the rotation is defined about an axis K, okay, so RK theta, then d RK theta by d theta, okay, the derivative of RK theta by d theta is equal to S of K into RK theta. So we have to find the unit vector that is defining that axis of rotation, and then or the vector that is defining that axis of rotation, form its skew symmetric matrix. Skew symmetric matrix into the rotation matrix is going to give you drk theta by d theta. Now you might be wondering why this is important. The thing that is important here is that the mathematical operation of taking a derivative or differentiation has been converted into multiplication of two matrices. So this is very important when we are talking about the controllers of robots calculating various parameters like velocities and forces and torques and positions. It is better to have multiplications and additions rather than you have integrations and differentiation. So here you have seen using a skew symmetric matrix. Now this has been proved mathematically. We are just simply taking the result here. D rk theta by d theta is equal to S of k into rk theta. So this is another very important result. R dot of t, that is the time derivative of the rotation matrix, is equal to the skew symmetric matrix of the angular velocity into the rotation matrix. So this is a rotation matrix that is varying with time. When the robot moves, its rotation matrix also varies with time. So the time derivative of the rotation matrix is equal to simply the skew symmetric matrix corresponding to the angular velocity omega of t into the rotation matrix. So this is proved like this. So suppose r of t is equal to rx theta of t. So this is a rotation matrix, rotation about the axis x through an angle theta. So an r dot, that is the time derivative, can be written as dr by d theta into d theta by dt. R dot is actually dr by dt. This is written in this form. So we know that dr by d theta, from the previous slide we saw, and since this is around the x-axis, so we can write x-axis is vector is I, we know. So dr by d theta can be written as S of I into r of t. Okay, so this is from the previous slide result, and d theta by dt is theta dot. Okay, so I'm just going to rewrite this theta dot into S of I into r of t. This is equal to, this is not very clear, so keep your notes with you. So is equal to, I'm just going to take this theta dot inside, S of I theta dot into r of t. So we had seen in the first slide itself, omega is equal to theta dot into k, where k is the axis of rotation. So our axis of rotation is I. So theta dot into I will give me what? Omega. So S of omega t into r of t, which is the result that we got. So very, very important result that simplifies the computation of velocity kinematics. Now we are talking about several links for the robot, several joints. Okay, so associated with each link, we know there is a frame. So suppose we are going to talk about the angular velocity of the nth frame with respect to the base frame. This can be written as a sum of the angular velocities of the various frames in the manipulator. So you simply cannot add all the angular velocities directly. We have to convert them into the base frame and then only add them. So the addition of angular velocities, this result also is proved mathematically, can be written as angular velocity of the first frame with respect to the 0th frame plus the angular velocity of the second frame with respect to the first frame, but rotated by the rotation matrix R10. Okay, plus angular velocity of the third frame with respect to the second frame, but again rotated by the rotation matrix R20, and so on till the n minus 1